So we extend our discussion since our previous session, what we recall. So just to recap quickly, we talked about a latch, and some of you asked me what's the difference between latch and the flip-flop, right? So I'm gonna once more tell you about. So latch, remember, is a level sensitive circuit or logic. Level sensitive, it could be positive or negative. Flip-flops on the other hand are edge sensitive, positive and negative or negative. So this is the circuit representation of the D latch. For instance, I have a data input and this is the transistor level or pass gate level circuit diagram, and the waveform we understood like this: when the clock makes a transition from level 0 to level 1, at that time whatever the value is D of D is, the Q will follow that. So D is equal to 1 here, so Q will also make the transition to 1. So that is how we show it here. Then clock, as long as the clock is at the level 1, so if the D is following 0, so the output Q will also follow 0. So D will always be transferred to Q when the clock goes from 0 to level 1. That's very simple in a one sentence. This is how the latch operates. On the other hand, look at here, this flip-flop, we use two latches. So what we see here, whenever the clock makes a transition from level 1 to level 0, so at the edge, as soon as it makes the transition, then that word we call it as a edge, E-D-G-E, edge. So edge of the clock, when it falls from 1 to 0, so no matter D was previously 1 and now it is 0, but Q is shown to be level 1. So it doesn't matter what is the value of input D, the Q is at the previous state, because this master slave is disconnected from the slave section of the flip-flop. So remember, from when the clock makes a transition from 1 to 0 at this negative edge, no matter what was the D and is the D, but the Q will remain in the previous state. But as soon as the clock makes the transition at the positive edge of the clock, so if the D at that time is at level 1, Q will also start to go to level 1. Why? Because D is now getting to the master output, and the role of the master output gets to, the value of the master output goes to Q. So D is 1 at the previous clock, so Q is also becoming 1 here. Similarly here, look again, clock is making transition from 0 to 1. So at that time, when it made the transition, D fall from 1 to 0. So the output which was previously 1, it also falls from 1 to 0, logic 1 to logic 0. So because that is how the triggering of master and slave is happening. So just to conclusion, remember always what is the difference between latch and flip-flop. Latch is level sensitive and flip-flops are edge sensitive. So just to summarize, always remember transistors, we use them, and MOS, PMOS, pass gate to build the logic gates. We use logic gates to build the latch. We know that how do you make the latch? We use the multiplexer or compound gates or tri-state logic to build the latch, 1-bit latch. And then we use latches to build the flip-flops and so on. Then we use the flip-flops to make the registers, counters, memory, etc. So this is how you start with the transistors and the logic gates, and you keep on designing bigger and bigger blocks. So this is how the VLSI flow will operate. So giving you a brief introduction about fabrication, we have already covered that. Now I am taking you slowly to the how actually they are manufactured and what is the meaning of layout, which is your job. So we know that this is a silicon wafer. I have explained to you before. It has about 15 to 30 centimeter diameter, right? And each individual CMOS is basically a die. This is called die. or chip, SI chip, and each chip contains about millions of logic gates or billions of transistors, right? And the size of each chip would be about, let's say, 100 by 100 micrometer square, so this small, because we are operating. So this is a wafer, silicon wafer or substrate that acts as a base to this individual silicon dies, acts as a support, and is also called as substrate, right? We have seen that. So let us just quickly revise how the transistor, if I want to fabricate CMOS logic for the inverter chip or the NAND chip or the memory or the latch or the flip-flop, how I will go to fabricate it. Why I am giving you this understanding? You are the physical design team or layout engineer team. So when you will draw the layout of bigger and bigger processor chips, system on chip, ASIC, and all these big chips, you got to have also a basic understanding about how things are manufactured in the foundry, especially the transistorized circuit. That information will help you to better understand your layout designs, and when you do the simulations, when you do the verification of your chips. So for what we use in the CMOS fabrication and the layout, we define the set of mask. I have already told you what is a mask. Mask is basically a layer indicated by the rectangles. That layer indicated by the rectangles tells us the area on the substrate in which that particular region will be fabricated. That region could be N diffusion, P diffusion, N well, P well, contacts, metals, polysilicon, gates, etc. So all these words, I believe, are now familiar to you all. These words, these masks and layers are familiar to you, because they are going to use to manufacture the different parts of our transistorized circuit. So we are talking about a simple transistor circuits, but remember, if you have a good understanding about a simple transistor layout, it is very easy for you to analyze a very big layout that contains millions of transistors, even the 10,000s of transistors or the logic gates will be very easy, because your foundations will be good. You have a good information about all the layers, mask, and all these things. So the size of the transistors and the wires that will be used to connect the transistor to each other to form the circuit will be set by these mask dimensions that we are using for a particular. Usually they are all in the nanometer size, because we are learning a nanometric CMOS VLSI. Okay, and that size is defined, is also called as a resolution of the manufacturing process. If you remember, I have explained you, this is also called as feature size. Often there will be advertisement about having required experience about feature size in 10 nanometer, 28 nanometers, and so on. These kind of things will be required, right? So they will use these words, resolution, feature size. So as a layout engineer, these are essential words that will help you to talk to your fellow people in the industries. So let's understand in a brief way how this transistorized circuit can be fabricated. So very simple again, if you recall the previous session, we start with the simple substrate, and then we have to perform a series of steps to fabricate a transistorized circuits, right? So the layers of the chips, different layers of the chips will be defined through this through a particular process, and that process we call as photolithography. Remember this word also. Photolithography is just kind of printing technique used by the VLSI industry to fabricate the chips. Okay, so smaller transistors are going to be fabricated because they are faster and they consume less energy, because we know that feature size of the transistor now is in the nanometers. So they are very small, ultra small, that the feature size is nanometer. That's why they are faster. I have told you why they are faster, and obviously they are consuming a very less power because less charges are required on top of the gate to turn them on and off. Okay, so what we do here is we perform series of steps. What steps are there? On the substrate we first deposit a material called as photoresist. This photoresist is basically insulating material. It's an organic polymer, right? So that we put it here, and on that we use the mask. I told you what mask is. Masks are basically a layers in the shape of rectangles. They help us to define the area on the substrate in which we want to fabricate the regions of the transistors. What the regions of the transistors we want to fabricate? We'll define where is going to be the N-well, where are going to be the diffusion regions for NMOS and PMOS and so on. So what you do here, you see substrate, you have on top of that a photoresist, and I here in these three places I put the mask because I want to fabricate a particular region into the substrate. So then I expose this system to a light called as ultraviolet light. So light coming all over the substrate, and the mask where I have placed it, the light is obstructed or stopped by these layers of the mask. And where I don't have a mask, the light goes inside, and the portion or the area where the light goes inside, right over here, that photoresist at that place gets softened, gets melted. And after that we see two kinds of structure. We can have two kinds of structure. Here, if the light that falls on the photoresist and that gets melted away, it means we can remove it. That kind of photoresist if we use is called as positive photoresist. So you see here, the where light did not reach, the photoresist remained here, and the remaining photoresist where the light fell, got removed. Negative photoresist would be on the other hand just the opposite, where the light fell, the photoresist in that area remained on the substrate, but the other places where the light did not reach, that got away from the substrate. So it depends on what is your need and all that. So we'll refer to the positive photoresist for examples. We'll assume that we are talking about positive photoresist. So you need to have a basic understanding about how these layers are used. For example, again, you see how many layers you need to fabricate using a particular, let's say you are, as an engineers, you have a job in your company to draw a layout for a CMOS inverter chip. So CMOS inverter is a single cell for which you are asked to draw a layout. And in that library, then you have a tool to use it to draw the layout. You go and invoke the tool as an engineer, and then you open the tool and you see already in your tool you have a technology library installed. That is called as tech library. So it tells you also the information. The library also provides you an information in what technology or what is the feature size or what is the resolution of the mask that will be used to fabricate your chip. So let's say it's a 10 nanometer. That's what you are working on. So you already have this information. Then you open the tool and open the library and you explore, and then you say, okay, I've got these layers in my hands, and using them I want to lay out the circuit or the mask of the CMOS inverter cells. And then you create one IP of CMOS inverter cell, then you create an IP of NAND cell, NOR cell, latch, flip-flops, and you keep them in your library as a designer, as a layout engineer. And then when you want to design a layout of big chip, let's say memory, controllers, registers, microprocessors, etc., you can refer to these IP cells. You will often hear these words, IP cells, that you have already defined and designed yourself, and you have put them in your library somewhere. You can then call them Just like in software engineering, you call the functions oftentimes to create a bigger code. You can also call these logics that you have already defined of a unit cells to create bigger logics, to lay out bigger logics. So you should be very familiar with this, how these layers look like and how the final layout. This is the top view. I have already told you that how the top view. You should really understand how the layout looks like, because on this layout only you have to perform verification of this chip. So again, NVEL, you already, I have told you that how the NVEL is looks like and where it is placed. Polysilicon, that forms the gate of the two transistors. N diffusion regions, P diffusion regions. If I have N diffusion regions, it means I also need N diffusion for NVEL. If I have P diffusion regions, it means I also have another area of P diffusion to have access to the P substrate. Then I have a contacts. This contacts basically helping me to have the cuts in the substrate in which the metals will connect to the respective regions, and finally I will be able to visualize the layout. Let's say you have drawn this layout yourself using this technology library. So once you know, you can draw a simple layout. You can draw a layout of thousands of logic gates because it's an automated process, and then you can verify that functionality. Okay, so look, this is now a top view, and here is your bottom view. Here is not the bottom view, it's the side view. So I give you 2 minutes just to understand how side view and the top view looks like. I hope you have studied in engineering the subjects engineering drawing. So in that you have this top view and side view, right? Isotropic views, all these views are there. So just take a moment, and can you the task I am giving you to relate this side view to this top view, and these are the layers that you have used to create this tool. Just take a moment and see if you see any question related to that. This is the cross section of the inverter circuit that you have actually used these layers and the technology to draw the layout of your circuit, and you are done, right? So you have used this is output, this is logic A. You see all these layers, how these layers are there. So you started with P substrate. I know it's a CMOS, so I fabricated NVEL. In the NVEL I will have PMOS transistor, so these are the source and drain. In the NVEL I need to have a body contact, so I got another region, I call it NVEL tap. Then in the P substrate I have NMOS. These are the source and the drain region of the NMOS, and I need to have its access to its body, so I have another region called as P plus substrate. This is the region I am calling it as a thick silicon dioxide, and it is there to avoid the metal contact connecting to making a short circuit, and at the same time this material SiO2, thick SiO2, is helping me to isolate all these individual regions because they should not be shorted, right? So this is how I see that my side view looks here and the top view looks here. You should be very good in visualizing and understanding these two views of your layout. Okay, ask me questions.
I have one question.
Yeah.
In the N plus diffusion, according to the side view, what we are seeing in the left side of this presentation, there are 3 sections, like the source, the drain, and the NVEL tap, right? But in the diagram, in the top view section, I can see only two places. I mean, 2 places where the diffusion is taking place. I mean, the middle one is the gate, I know, but why is the gate section is included for the diffusion? Like, if you can understand.
Okay, one more time I explain you. See, this is a top we start with, and we try to relate with the side view. So what I see first in the P substrate, let's say this is my P substrate. This was a P substrate. And in the P substrate, I firstly fabricated N well. So this is the gray region, I see that. So here is my N well, right here. Clear? Now, in the N well, I want to fabricate a PMOS transistor, obviously. So where are the diffusion regions? This is the mask for the diffusion. So look at its alignment. This is the mask for the diffusion. And source and drain will be separated and automatically created as soon as I draw the poly mask on top of it in the middle of source and drain. So look at the side view. This is my source and drain, and as soon as I draw the gate, polysilicon is coming on top of that. On the top, this is side view. I see that source and drain are automatically fabricated. Now I want to have the access to the body of N well, which is a body of PMOS. So where is the mask for that? This is the layer I am using, and look at its alignment. Where is the alignment? Here, this square. So I got the body of the PMOS here, right? This is the body. I am done with the PMOS. Same I will repeat for the NMOS. Understood?
Yes.
Okay. So we move to next slide. So this is very simple, and once you have a good understanding about all these things, you will be able to interpret, analyze a bigger layout. That is the key. And remember, these layers will always be handy. Now you got to also have a good understanding about, although these steps are of the manufacturer, things are going to be done in the foundry when the chip is sent for fabrication, but you got to know, you got to understand how things are done at that end, because oftentimes you have to be compliant with the foundry rules. When the technology comes to you, library comes to you, you have to obey the rules and regulations of that technology. You cannot violate. That's why we will also learn in detail DRC, design rule checks and all that. So for that, this is also a quick synopsis of you, giving you an overview about how the basic transistor circuits will be fabricated after you lay out them in your tools and you send it for the fabrication. It is also important to understand how they will be fabricated. So what you do here, you start with the P substrate. The foundry engineer will do that. They will start with the P substrate. They want to, the first task is to create an N well on a bare P-type silicon wafer. So you are given, if you are not a layout engineer, now you are, let's say, foundry engineers or a team of them. So you are given a bare P-type silicon which is 15 to 30 centimeter in diameter. You are in the clean room of the company and you are doing that. So look, here you are bare substrate. So first thing you grow a thick oxide is called as silicon dioxide on that, on top of the material. On that again, as I said, you deposit and grow a photoresist. That's again the polymer, organic polymer material. Why photoresist? Because that's the step of patterning your design. You want to pattern. It's just like you are drawing something on a piece of paper. So you have to decide on the area of a paper, on which area of a A4 size paper you want a particular design. You have like flowers, you have so many things on a piece of paper you want to draw. So you want to first choose the area, which area will have what, right, in that case. So photoresist is there, and then you see this photoresist is removed from this portion. So what step they have done here, they actually put a mask in this particular area, and then they expose the whole system to the light, ultraviolet light. So you see the light, actually the mask is put over here, or I would rather say, if you are using the positive photoresist, they put the mask, let's say here, and the mask let's say here, and this portion, and then system is exposed to the light, UV light, all over, all over, all over. So the portion where the mask was present, the light did not reach the photoresist, and the remaining portion where you did not have a mask, the light reached, and this particular area got away. The photoresist got melted, softened away. So you got rid of it here. Okay, so that we call it as, let's say, a positive photoresist, because that's what we understood how the positive photoresist. Negative photoresist will be opposite of that, right? The photoresist, if it were negative photoresist, the photoresist will remain here, and the rest of the area, the photoresist will go away, right? So just try to understand which photoresist we are using. But just for a simple sense, let's say we use the photoresist, we put the mask here, and in this area, and this area where the light came in directly, the photoresist got exposed, and this portion, the photoresist got away, melted away. Now once the photoresist got melted away, why this area? Because here we want anvil, right? As we are going to this step now, so this is the area. The next step, I put this wafer in the hydrofluoric acid. This is HF acid, and this is the wafer. Let's say I put the wafer, and then in this portion, the SiO2 hydrofluoric acid is known to etch the SiO2. This is the chemical process step that you are doing. So SiO2 will be etched away. Once that process, that step is done, you just remove this photoresist. Then you just rip it off, right? Take it off. So this is the final figure that you have. So you have bare p-type substrate. You see, you started with this substrate, and final step number F, you are here, you have SiO2 except this portion. Why you don't want SiO2 here? Because this is the area you want anvil to be fabricated. So what you do here? Very simple. You use two different approaches. One, if you remember, I said ion implantation, and second procedure is diffusion. So you just bombard the dopants. Dopants go deep inside the wafer until the depth you want, and then finally you see the area is done. Right here the area is done, anvil is created, and after that you again etch this remaining oxide, and final figure that you have is the anvil with the p-type substrate. So just take a look at this final etch and the figure number A. You don't have anything here, and you got your anvil fabricated. So these steps you will repeat to fabricate all the regions of your transistor. You have so many regions to fabricate, like P plus here, P plus here, and you got to fabricate NMOS also here, right? NMOS, and then you have got to fabricate polysilicon. So many things are there. So step by step you always do these things. But for engineers in the PD team, layout team, it's a good if you have a good understanding, or at least a basic understanding of all these steps that are happening in the foundry. So you started with creating anvil in the p-type silicon, and you know that the anvil will require dopant into the substrate here, and it changed this substrate from p-type semiconductor, and this portion of this p-type semiconductor got changed from p-type to n-type, right? And this is how the steps happen. Excuse me. Once that is done, I have already told you these are all trivial details that you may or may not want to keep detailed attention to, like when you grow the oxide, what temperatures they use in the foundry, like about 900 to 1200 to grow this oxide here. Okay, and how this oxide is grown? The oxygen, SiO2, is silicon dioxide, so there is a reaction between silicon and the oxygen, O2 atoms on the wafer. Okay, and then oxide is patterned, as I said, this oxide is patterned to define the anvil, because this is the area we want that. And I also explained that then that photoresist got exposed to UV light because through the N-well mask they used, and that allows the light to pass through only where the N-well should be, and the photoresist gets softened and then it is removed to expose the oxide again. Then oxide is etched with the hydrofluoric acid, and the remaining photoresist is then taken out, and you come at this figure, and finally this is how the veil is formed. And again, how many things? Only N-well out of this we have successfully created. Now remaining steps are to be repeated to fabricate polysilicon, to define them, to fabricate diffusion regions, to fabricate contact and melt. So how to do that? Again, use the mask which will specify where these components will be manufactured on the chips. And look, their placement is basically deciding where each of these components, look how they are placed. N-well is placed here, this is the substrate, this is the area, and in each, just like a piece of paper, I am putting the N-well here, polysilicon here, NMOS transistors here, PMOS transistors here, right? N-well here, P substrate here, and the contacts, and then the metal. So the mask will be used in all these things to define your sections out here. Okay, just a second. So next step, see now how what we are doing here is the polysilicon. We want to grow the polysilicon. So again, what we have done, we just grew the thin oxide, very thin layer of a oxide again right over in the middle, and on top of that this polysilicon is also grown. So again, this happens in the clean room foundry. So why we want polysilicon? Because we want to form the gates of the transistors. So this polysilicon layer will be grown through the chemical vapor deposition process, and then this polysilicon is heavily doped. Why? Because this is a semiconductor and we want the conductors actually. So when it is heavily doped, it will act as good as conductor, right? I have told you already, in modern technology today, we use polysilicon instead of metal for gates, because ultimately our structure is metal oxide semiconductor, and then we call it MOS or MOSFET, MOSFET, field effect transistor. So always remember this. Okay, so
Hello.
Yeah.
So what is the main difference in using polysilicon and metal? So why they constructed polysilicon rather than metal?
Yeah, in earlier technology, in the let's say a few decades ago, 1970, when the MOSFET, integrated MOSFETs, they got fabricated, they used to use metal to grow the oxide on the top of the semiconductor, on top of the transistor. So this was metal, this was SiO2 oxide, and this was polysilicon, the substrate, p-type substrate or n-type. So that's why they call it a MOS transistor. But nowadays you use poly, SiO2, and again the p silicon. So metal got replaced with the polysilicon. Answer to that would be because of some fabrication ease. Nowadays, as I said, we don't use metal for the gates, but rather we use polysilicon, and when it is heavily doped, it acts as good as conductor. And the reason for that could be ease in fabrication, and there could be some other advantages of using polysilicon, because also when you fabricate the integrated circuit, you have to perform some steps at very high temperature. So polysilicon, growing the polysilicon requires less temperature. Growing the metal as a gate requires high temperatures processing steps. So those could be the reasons. And there could be some additional reasons also for using polysilicon for gate.
Fine, sir.
Okay?
Okay, sir. Okay, sir.
Good. So, so what we are seeing here, look, this the wafer is pattern again with the photoresist. Can you just imagine from the figure A, we come to figure B, and we see now for the portion except this and except this, nowhere the other area they are not present with the oxide and the polysilicon. Only at these two places we got the polysilicon and the oxide on top of each other. Why and how this happened? Again, what we did is that we patterned this wafer with the photoresist and the polysilicon mask. Mask was placed at the places where we don't want polysilicons. Right here, and the right here. We want polysilicons here, right? So the mask protected the UV lights not to pass through it, right? And therefore the other areas where the light went passed through it, the photoresist got softened away, and then we etch the polysilicon and the silicon dioxide from those area. Which were those area? Here, this one, where we don't see polysilicon, right here. Did you understand this step? So so polysilicon gate on top of the thin oxide, we can see it in the figure B here. N-well is already formed, and then now the next step is to fabricate the N plus diffusion regions. Where are the N plus diffusion regions? N plus diffusion regions are to be fabricated to fabricate which type of transistor? N plus diffusion regions, NMOS, that's correct. N plus diffusion regions we want to fabricate. So from figure B we come to figure C. What we do see here, we again grow a thick layer of SiO2 on top of this, right? And then again next step, which region we define, which region on the substrate we want those N plus diffusion regions. Obviously this is my P substrate, I want N plus diffusion regions here and here. Look at the figure here, here they will be fabricated. So come back to figure C, somewhere here, right, I want them to be fabricated. So because that's my transistor active area and the well contacts also. So what I'm doing here now, I have grown the thick oxide here, and then can you tell me how we go from figure C to figure D? Look now what I see in this area. Again the light fell, photoresist got etched away, and then I put the wafer in the silicon hydrofluoric acid, and the silicon dioxide got etched away from these areas, right? And the remaining area got protected by the SiO2 because on top of that photoresist was present. And then I again took off the photoresist from top of the SiO2 also. So this is how, because here also on active area of N plus, active area of N plus, and active area of N plus. So this is how I again repeated the same procedure. Now once that this figure D is available, I got the ion implantation. So what I did here is very simple again. I used the ion implantation. I introduced the boron dopant up to the depth I want, and that's how I got this one. Once I got the diffusion process complete, I again etched this remaining oxide, and final form of the figure is this one. So what in this particular slide I got two steps done. I successfully fabricated the gates of the circuit, and I successfully fabricated the active area of my NMOS, and I also successfully fabricated the body contact of my N-well, which is the body of PMOS, right? Same thing I will repeat to fabricate my PMOS transistors. Again I will deposit a thick SiO2 on top of the entire wafer. Then again I will put the photoresist on top of this one. Then I will define which area I want to fabricate P plus diffusion regions. So I know that, okay, these are the areas I want the P plus diffusions, P plus diffusions, P plus diffusions, right? Then I put the mask in these areas, in these areas, and in these areas, right over here. Then the light comes all over the place, all over the place, all over the place, ultraviolet light, and it's a positive or negative photoresist, depends on that. The light falls on all these portions, the photoresist will melt away and the light will be blocked by the mask over on those regions, right? Light is not falling. But I just did the reverse step. I will not put the mask on the area I want to fabricate these P plus regions. Rather, I will put the mask in the areas where I don't want these regions to be fabricated, right? And because then only the light will fall through the photoresist and photoresist will be melt away. So it just, you can recall what previous steps we did. So final figure would be like this. I have got this P plus regions done, and these oxides are there. This is thick filled oxide. This thick filled oxide is helping me to avoid the contacts between individual regions, because the source and drain, if they are short, then obviously the transistor will not work. And final step would be, I will pour all the metal. I will pour the metal all over, because that's how I will have the physical contacts, physical connections. And this is how finally the circuit got completed. So any questions so far about the fabrication? And here we successfully complete all the fabrication steps, and now in this session we understand that, okay, we thoroughly understood how to use the transistor layers to draw the layout of the circuit. Because if you are good at drawing the layout and understanding the layout of one particular cell, then you can analyze and draw it for the bigger cells. Then I also explained you one by one all the steps involved in fabrication of this CMOS layout. Because when the layout is done, you do the verification. It means you pass some checks, you do DRC, LVS. Once your tool says thumbs up, you send the chip file to the foundry, and these steps, fabrication steps that I just explained you step by steps, will be performed at the manufacturing plant to fabricate your chip. So you see, I gave you the overview and understanding about one particular layout of one cell, but they will do the same action at the same time in parallel to fabricate such millions of transistors, or even several millions of transistors at the same time. So this is the technology through the photolithography they will do. So far any questions you have, you can ask me. If you haven't understood, this is very crucial, important for you to understand. Let me know. Any questions or anything you want to understand more, or you think you can also have your comments. If not, we move to next slide. Now what I'm going to teach is, like I said, when you receive a library from the foundry, you have a tech library, and then you will use that library. You will already know what is the feature size or resolution. It means the transistor size basically, by which you are going to drawing your layout, your physical design, you are completing that. So some manual layout if you are expert in manually drawing the layout of your unit cell, manual drawing, using the design rules in terms of lambda. So lambda would be L by 2, where L is the resolution or the feature size of the, or let's say the channel length, if you recall, I have explained you. So using these simple design rules, if you become an expert to draw the layout manually of your unit cells, let's say inverter, NOR, NAND, and so on, and then you should be able, you are also good at drawing the layout for latch, flip-flops, and you already know how to use the layers. All the layers I have shown you. How many layers I have shown you so far? Mask layers.
6.
6. Good.
6.
Good. That's really good. Poly, P plus, N plus, NOL, contact, metal. In some technology you can have additional layers also. For example, I have told you here I have given you only one metal layer, so you call them as a metal. In some technology you will have so many metal layers. Let's say you can have from metal 1 to metal 6. We'll see in more detail what are the use of them. So if you are good in understanding these things and quickly able to become an expert in manually drawing the layout, and what's the purpose of knowing, you having that knowledge and having that skill? Because you will be able to understand what is this lambda rule, quickly able to know the size of your chip, of your unit cell, what is the length and what is the width. Because when you do the floor plan for a big chip, you do the place and route for the big chip, then one thing you need to do, that is area estimation of your chip, because that's how will be, as a layout engineer, you will be constrained by that rule. You have a given area, minimum given area, I would say maximum given area, you cannot exceed that. You have to fit all your blocks, all your unit cells within that given area, right? Within that given area. So this lambda rule comes handy at that time to help you quickly understand and have a basic estimate of your chip area, and also the all fundamentals there. So lambda design rule, I have explained you already, is generally the half of the minimum drawn transistor channel length. You have a transistor, I know, I have told you, and source to drain, you will have minimum channel length. Okay, how fast the transistor. So if you are given, you are working with 180 nanometer process. So it has a minimum polysilicon width of 0.18 micron, which is nothing but 180 nanometer. So lambda will be half of that, right? So why minimum polysilicon width if it is 180 nanometer? Why we say that the polysilicon defines the channel length and therefore the lambda? Why? Because I have explained to you, when you have fabricated your source and drain, let's say you have source and drain of your transistors, right? Source and drain. So this is the mask for diffusion, P plus or N plus. Once you do that, as soon as you draw the poly on top of it, because you will also use the mask for the poly, as soon as you draw the poly on top of it. So this width actually of the poly is nothing but your length of a transistor. So look, this is the top view, and how the side view will look like. P plus or N plus, whatever, and this is your poly. So look, this is top view and this is side view. So this width actually of the poly from the top view is your channel length in the side view of a transistor. So remember this. So minimum polysilicon width is 180 nanometers, so lambda will be half of that. So designer, layout designer will often describe this process by its feature size. So feature size refers to the minimum transistor length, so lambda is the half, and this rule will tell you about what is the minimum width to avoid breaks in a line. Okay, uh, it means it will also tells you the distance between the two lines when you draw the layout. It will also tell you the minimum spacing to avoid shorts between the line. We'll see that in a moment. It will also tell you the minimum overlap as an engineer, as a designer, you can have to ensure that two layers completely overlap and all these things. So we'll see by means of some diagrams. Here is the diagram. So let quick recall. The set of rules are given to you now. This is an example, but when you physically draw the layout of your chip, as an engineer, you are actually doing it. You will come across the same situation. You have to refer to the manual of your set of design rules for the layouts. So now you are given two metal layers, for example, and you are given anvil process. So this is very important. What is very important? Like I said, how many layers we had in the example earlier? 6 layers. How many? What was the substrate? P substrate. So in this slide that is currently shown to you, we have like 2 metal layers. So we have more than 1 extra metal layers. What is the use of that? Can anybody tell me? I have in this process I have 2 metal layers. What could be the use of that?
Power readings.
Yeah?
Power readings.
Power readings. Power, you mean power?
Yes, sir. Power or ground.
Yeah, metal lines we'll use to connect the transistors. They are just wires, right, in the circuit, the metal. So they will help
Yes,
us
sir.
to connect the transistors together, let's say 10,000 transistors, and then we'll make a chip, right? But the advantage of having more metal layers is obviously you have choice, flexibility during place and route of your chip, because you have extra metal, so you can have the one metal all horizontal lines. Let's say when you have a chip area like this, so you use the metal one all horizontal lines, and then metal 2 you can have the overlapping on top of that, so they are not shorted. This is M2 and this is M1, metal 1, and so they are just overlapping but they are not shorted. So you have flexibility as a layout engineer in the given area. Because of the extra metal layers, you can have them on top of each other. It's just like a multi-floor building. Did you understand?
Yes, sir.
Yeah. So again I said it's an annual process. What is annual process? So it means I understand it is a P substrate I am given, and in that it will have annual. So layout engineer will quickly understand what he is given, what library he is working with, what design rules he has to follow. So what are your design rules? First rule, you need to adhere and follow all these rules while drawing your layout. Of course tool will do it for you. Tool will follow all these rules, but still there will be some instances where you have to interfere, because that's you are engineers of that physical design. So at some instances you have to manually adjust the things. At that time you will do place and route for some. That's why we sometimes use this application specific ICs, application specific integrated circuit. So all the chip, some portions of the chips you have to step in, take the charge and manually route those cells, and rest of the cells, the big cells or short or middle, they will be automatically routed by the tool. Again, you will have to inspect them and verify them, but some special attention you will have to pay. That chip is called as application specific IC. Other chip I have explained you called as, what is SoC?
System on chip.
System on chip, right? And what is this? FPGA, field programmable gate array, is also is not what we want to learn for this course, but just remember this is field programmable gate array. It's also a digital design. In digital design they use it, right? So you see now you have metal and diffusion. They have a minimum width of and spacing of 4 lambda. So you got to see that where is your metal and diffusion. This is metal layer 1, this is metal layer 2, this is diffusion, this is polysilicon. So as a designer I got to follow the rules. What is the rule? If I'm manually routing this layer in my chip, this rectangular if I draw, so I will as a designer cannot exceed its width more than 4 lambda. So can anybody tell me, if I am 180 nanometer, what is the actual width of this metal layer? Yeah, try. I am using the 180 nanometer and I draw the width 4 lambda. So what is the actual layer that is here? What is the actual dimension of this metal layer?
0.02.
Lambda will be 90 nanometer, right? L by 2.
Yes, sir.
So 90 times 4, 360 nanometer would be the actual width. Right? Correct? Or a mistake? Yes or no?
Once again.
Once again, okay. What I explained to you, lambda is basically, I have to follow the lambda rule to manually draw my layouts. So lambda I know that L by 2. What is the L I am given? 180 nanometer for example. So lambda is half of that, 90 nanometer. Now I said using lambda rules I am drawing the layout. So I first draw the layer because I want to create this physical design. This is the physical design of my CMOS inverter. So for that I am drawing, let's say I draw the metal of this length and width. So rule says I have to draw it minimum 4 lambda. I cannot have 3 lambda or 2 lambda. Minimum it should be 4 lambda. So I drew it. And now I want to know what is the actual dimension, physical dimension of this rectangle that I just drew. So 4 times 90 nanometer, 360 nanometer, right, is the actual width of this. Is clear or not?
Okay, sir.
All of you are getting, this is important for you because how will you estimate the area of your chip? This is a simple chip. Let's say I am drawing the chip of CMOS inverter. So if you understand this, you will be able to understand the estimate of big chip, let's say a processor and all that. Okay. Any other questions you have? Okay, so that is it. We'll explore this more in detail tomorrow, about layout and all that. So we'll speed up a little more, and we'll see remaining part in the next section. Any questions you have?
Sir, excuse me, sir.
Yeah.
Sir, yesterday's class in 4x1 marks.
What?
In yesterday's class,
Huh?
we implemented 4x1 multiplexer now, sir.
Huh?
In the tri-state gate, why we use bubbles?
In the tri-states, why we use bubbles?
Sir.
So bubble says that it's the inverting type, right?
Yes.
Yeah.
Inverting, I know, sir, but why we use inverting?
That was the implementation that we did. If you want non-inverting, you don't use the bubble or put extra inverter in front of that circuit.
Okay.
Any other question?